So welcome to our review. As agreed, we got another virtual lecture here. Gives me another chance at editing some videos. Yeah, this is going to be the wonderful key. So we've got some mixed circuits here and some other various types of circuits. So we're going to go and analyze them and do some simple math, hopefully. And our first circuit up is, this one. So if you're staring at this on a test, you should figure out if it's, series, mixed, parallel. What kind of circuit is it? This one you guys should probably see quickly is a parallel because it has 3 parallel resistors. Yeah. Also it has branching paths. If you look here or anywhere, you can go down or right, so it has branching paths. That's because it has those branching paths. Yeah, parallel by definition. So let's go ahead and calculate total resistance, then the total current, then the total power. For the total resistance, you got these 3 resistors, all parallel, so you can literally just go 1 over 120 plus 1 over 45 plus 1 over 360 inverse 1. If you don't remember where this equation comes from, it comes from the equation of R parallel is equal to 1 over R1 plus 1 over R2 plus dot dot dot. You just keep adding resistors until you're done, and then you flip it. So we got that thing right there. It's beautiful. It's, you could technically find a common denominator, add them, and then do some fraction math. Or we can grab my calculator, which I will be right back with. Well, I got a calculator. It took a second, but yeah, let's go and do this. So we got, also you could, again, this can multiply to 360. This can also multiply by 360. In fact, if you do 10, that's 450. Then you take away 2 to get 90 less. That'd be 360. So this would be 8. That would be 3. That'd be 1. Then you get 12, and you flip it, and it'd be 360. Anyways, but regardless, let's just do it this way. This way is easier. So you could just grab a calculator and add the fractions. I didn't mean to hit there. Oh well, add the fractions. Plus 1 divided by 45 plus 1 divided by 360. You enter, you get that number, and of course it says inverse 1, so you can hit the inverse 1 power on your calculator, which just flips it, and you're going to get 30. So our resistance parallel is 30. So there's our resistance. Cool. We need some more things, so let's keep going. We also need to calculate the current and the power. She's right next. So power. No, I mean not power. So current. Although you could do power, it doesn't really matter. But current. So we know we have Ohm's law. V equals IR. We want to solve for current. So let's go ahead and rearrange this. So I is equal to V divided by R. So we're going to take the voltage, which is 240, even though it's AC, it doesn't really matter for this problem, but 240 divided by 30. We get 8 amperes, which is a very large number, but for current, to be honest. But 8 amperes, 8 amps. Last step we have is power. We know that power.
Pardon the interruption.
Sorry about that. So power is equal to PIV, current times voltage. There's other equations, but we're using this one. You got current right there, you got the voltage right there, so 8 times 240. 8 times 240. That's a lot of watts. Most components we have would definitely explode. But there you go. Got parallel resistance, current, power. Cool. So that was that's number 1. That's just a parallel circuit, pretty simple. Next, this next one we actually have is a mixed circuit. Mixing's a little bit more tricky. It's totally a mixed circuit. It's mixed because these are series, but these are parallel. So it already has a series and parallel, making it mixed. It has a branching and non-branching part. path, so it's mixed. So we're going to start by, of course, breaking this into many parts. First part is start as far away from this as we can normally. That's a trick I like to go with, although others don't have to do it that way. But these two, these are definitely series. So if you remember the rule for series resistance, you just add them, which is real nice. So in this case, our series resistance for these two, which I'm going to call 1, because there's going to be multiple steps, or 1 is equal to, maybe we should call it A. Let's call it A. That separate, 1, 2, 3, whatever. Separate the numbers from the letters. So this is A. This is part A, junction A. So you're going to add those two. You're going to get 10 plus 10, which is 20 ohms. So basically, these two resistors have merged. And instead of being two resistors, they are now just, this is a line, this doesn't exist, and this is at 10, this is now 20. Now the circuit is just resistor, nothing, resistor, resistor here still, and resistor. So next step, looking around, these are different. These are parallel. Again, this doesn't exist anymore, so you got a 20, you got a 50, parallel. This is a parallel circuit. So we're going to use our parallel equation, which is up here. So parallel, for what we're going to call very creatively, B. So parallel resistance is 1 over 50 plus 1 over 20 to the inverse 1. These have a common denominator you can reach of 100, so let's go 100. If you do that, you multiply this by 2, you multiply this by 5. Ooh, this is going to be not a fun one, though. Let's just use a calculator. We're going to get a fraction. But let's do it. 1 divided by 50 plus 1 divided by 20 inverse 1. There's our fraction. Like I thought, it is 14.28. If we want to do this correctly, we'd be using sig figs, which is 2 in this problem, right? No, 1. Because that some of these only have 1 sig fig. But we're not going to do that. We're just going to do it the old-fashioned physics way of this, keeping unnecessary decimals. So we're going to round it right here, 10th place, just because. Not correct, but it's fine. 14.3 ohms. If you're just learning, it's easier just to round there. So we got that. So we got these two resistors now. Now this has caused this to merge with this, so these no longer exist. So this is gone. And now we just have one resistor here. And instead of having 50, it is now 14.3. So this circuit part is gone now. Now it's just 3 resistors. And these 3 resistors are, yeah, you probably guessed it. I could totally hear you through the camera. These are series, right? So these 3 resistors are all in series at this point, which I'm going to call very effectively C. Since they're series again, RC car is equal to 200 plus 14.3 plus 15, which is often 229.3. The joke of it's often is sometimes you mess up and then your math's wrong, and that's sad. So this is actually the same thing as the total resistance. This is the same thing as the equivalent resistance, because we've simplified this all down to 1 resistor left. So this RC part here will make all these resistors merge into 1. So now it's just a battery in 1 equivalent resistance, which is this value. So I'm going to circle it. You always want to circle your answers so we know where we're stopping. Next, you want to do the same thing. You need total current, total power. So we're going to use the equivalent resistance to solve for those. Total current. Again, current we already know is equal to V divided by R, because we solved for it up here. So V divided by R. Okay, so we have 120 volts. Hey, that's American. 120 volts divided by 229.3, which is 0.52. Rounding, of course. So 0.52 0.52 amperes. Cool. Next, we want, again, power. Power, if we look back up here, is current times voltage, which is going to be the same thing as last time. You got 120 volts, you got the current of 0.52, and multiply those two, which is going to be roughly half, which is going to be almost 60, but let's find out. Times 120. 62.7 or 62.8. Don't forget the unit of power is watts. Unless you're American, in which case you should use horsepower. Joking, of course. Don't use horsepower. No one uses horsepower. That's insane. So there we go. We got problems 1 and 2 done. We got a parallel circuit, and we have a mixed circuit. We calculated the equivalent resistance, total current, total power. Cool. Next, let's see what other wonderful, not torturous problems we have. If you flip that page in that review packet of Happiness and Joy, we got hey, that's capacitance. It's a good friend using some capacitors here. These are in series. Now, most of you might remember, capacitance is nice in that it's, if you know the equations for resistors, you know the equation for capacitance, you just flip them. In other words, the series capacitance equation is the same as the parallel resistance equation, but you replace resistors with capacitors. So you're just adding them and inversing them. So again, this would be the parallel resistance equation, but for capacitors, it's series. So we're going to do this. So this series is 1 over 4 plus 1 over 3 plus 1 over 6, which they all have a common denominator of 12. That's something they can all reach. I'm going to try without a calculator this time. Maybe it'll work out. Maybe I'll need my calculator and be sad. We'll find out. So we're going to multiply this by 3, so this will be 3 over 12. We're going to multiply this by 4, so this is 4 over 12. And we're going to multiply this by 2, so this is 2 over 12. Now when we do this, that's 6, 9 over 12. Don't forget you're inverse wanting all of this. Still get a little bit lazy every now and then, but it's still there. So afterwards, you're going to flip it. So when you flip it, what you do is 12 over 9 now. That gets rid of the negative 1 power. So you could do you know, simplifying it a little bit more, and then take out a factor of 3 out of both these. So this is going to be the same thing as 4/3. Which is the same thing as 1 1/3. But get out your calculator, and you're going to get like what, 1.33333333. Yep. So this is 1.3 repeating. Don't forget the units were microfarads. That's what we use. That's what sticks around. That's the equivalent capacitance of this circuit. Similar to resistance, not actually different. Not all. Next, we have some components we've used in a lab. So this picture right here, even though you might not recognize it or remember it, is the picture of a resistor. That's what squiggle lines mean. It means you're resisting things. Oops. And this one right here is also a resistor, but a special kind called a potentiometer. I'm going to spell this wrong. I spelled it wrong for sure. Potentiometer. It's a potentiometer. Spelled wrong, probably. Luckily, it's not that big of a deal. I'll correct it in probably the video. But we got a potentiometer and a resistor. We also use a transistor, which is a changing resistor. We also use the cadmium sulfide photoresistor, a photoresistor. So we've used basically all resistors and capacitors. But mostly resistors, right? That's the main component we've used in LEDs. So next, we got this one. Hey, it's capacitors again. It's capacitance. It's a good old friend from up there. This is different, though. That's not series. They're parallel to each other. So this is parallel, clearly. You can also see it by, again, branching, right? this can go this way or this way when you reach this point. Same thing over here. They can, it's parallel. You can go multiple paths. So this is parallel. You got 3 of them parallel in a row. So parallel capacitance. It's the same thing as series resistance. So that means that you're adding them. So we're going to go ahead and add them. So you get C parallel is equal to 0.1 plus 0.2 plus 0.3, which is the same thing as 0.6. Don't forget microfarads are still around, so microfarads. Probably not the best handwriting, but it is my handwriting. There you go. So that's not hopefully too bad, but it's the same thing as the other page, except the equations flip and you're replacing R's with C's. Not that bad though. So this is probably an easier page, hopefully, the review. And now we have one last page, which is right here. Now this last page, we're going to look at for a second. So this last page, we're going to take a glance at, and let's see what we got. Well, you want to check the watt rating, right? And see if these components explode. So we're going to have to figure out the current going through the circuit and then check the watts of each component. We're going to have to remember the junction rules. Sketch a circuit. Oh, that's just drawing. That's easy. Build one of these 3 circuits in the PowerPoint. So that was similar to our lab. You either can build a parallel LED circuit, a fitting LED circuit, or a potentiometer buzzer. I think will be the ones that will be on your test. We'll see. But I'll give you an option. Easiest probably going to be 3 parallel LEDs, so I'll show that one when we reach it. So this first one right here. It's not the worst. It's not the worst thing we've seen. It's another resistor thing, right? It's a bunch of resistors. Is it mixed? Is it series? Is it parallel? Well, let's look. Starts out, yeah, series, parallel, series. So it's series and parallel, so it's mixed. It's mixed. Which, of course, it's mixed circuit, so I mean, it should be mixed, right? So let's find the total current. That'd be a good first start. That way we know, like, how much current's breaking apart. So total current. If we simplify this into a series here, we're going to do 1 over 3 plus 1 over 5 flipped. So we're going to do 15. You're going to get 15 over 8. That's just ugly. So let's get out our good old friend, a calculator. 1 divided by 3 plus 1 divided by 5 inverse 1. We get 1.875. Okay. Here's the. So of that number we just got, we're going to write it down and, do the next step. So these merge into one resistor, which is basically going to be right here in the middle. Now I am going to use sig figs in this problem because I'm lazy. So 1.875, well, these all have a 1 sig fig. That has 2 technically, but for the resistors you have 1. So least number of sig figs, 1. So we're going to round this to 1 sig fig, which makes it 2, which is close enough. So this is 2 ohms, right? 1 sig fig. Okay, so next we're going to figure out the total resistance. Well, that's in series, so 8 plus 2 plus 6 is 16. So the total resistance, or equivalent resistance, is 16 ohms. Next step. You want to figure out the total current and total, well, not just total current. We don't really need total power. We'll figure that out later. We got to figure out the watt rating of each of these, so I mean, it's not the most helpful. But current we do need. So current is voltage divided by resistance. So we need 12 divided by 16. So 12 divided by 16. Which is nice, because those are both things of 4, so it'd be 3/4. which means that the current is 0.75 watts. I mean, not watts, sorry, amps. Now, if you do the same thing as last time, we could do these number sig figs and make that 0.8, but let's keep it like that for now. I'm lazy. Looks nice. Next, so now we do everyone's favorite thing ever, a thinking game. This is not watts. That is not watts. We can figure out the total watts, but that's not the watts of each individual component. So let's figure that out first. For this, we know that the current of 0.8 is going through this circuit, right? So it's just leaving this battery, just going up and around this circuit. This current is, so far, 0.75 actually without rounding. And this current reaches its first resistor. Now, so far, it's in series, right? Series rules state that the voltage changes, but the current is the same. So the current actually goes through here, sticks at 0.75. It hasn't changed yet, right? Because it's a series so far. So when it reaches here, this is where we get to the fun part. This, 0.75 still, reaches this point right here. Well, that's branching. These are parallel. That means that at this point, you have two different currents. We'll call one current, which goes through this resistor, I1. We'll call the other current, which goes through this resistor. Let's use red, maybe. Orange, not red. That's going to be the most clear colors I have left. The current that goes through this resistor, we'll call very creatively I2. I know, it's shocking. I'm not naming it like IB or something. Just I2. So we got two different currents. When they branch back together, at this point, we know they have to fuse back into being the same thing as this side, because the current rules, right? So this currents merge back into 0.75 and return back to the battery at 0.75. Cool. Conservation of current, right? You can't just change unless we're using some kind of nonlinear component. But for now, they can't change, right? That violates physics. You can't just create matter. So we got that. It violates chemistry too. But yeah, we've got this so far. Cool. So there's current this side, current this side. These are different. We know these are the same. So we can actually start calculating some things, right? So I'm going to name you, I already used blue, black, and technically I'm using these colors for these two. So you're going to be orange. So our orange resistor up here is going to be resistor BC, because that's point B, that's point C. This resistor is 8 ohms. We're going to figure out the power at BC, right? Power BC. Power at BC is going to be, well, PIV, right? Current times voltage. We know the current's 0.75. Do we know the voltage? That's our first question. So far, no. Can we figure out the voltage? Yes. We know that the voltage is current times resistance. So we got 0.075 times the resistance of 8. So 0.75 times 8. 6. Right? So 6. So we know that this has a voltage of 6 volts going through this. With that voltage, we now know that this has a power of 6 times, again, 0.75. 4.5. So we know that there is a power of 4.5 watts for that first component. Which honestly means this first component is going to explode, which means that there probably wouldn't be power reaching the rest of the circuit because it's in the way of the rest of the circuit. But let's ignore that. Let's keep going, right? This first component does, in fact, explode. So this explodes. It's sad because BC. Sad, such a sad time. Anyway, so we got exploded. This resistor totally explodes. Probably not a resistor, to be honest. It's probably like a lamp or who knows, some kind of electrical circuit that has intrinsic resistance of that, or maybe even just an inductance of that, or whatever. It has the complex impedance that gives you resistance of that, but you guys don't know what that means, so I'm ranting. I'm ranting for no reason. Maybe you do know what that means, which congrats. That's great. Now let's go for the other easy one. This one's also easy. What do you use blue? What do you use black? I think I need another color. Let's go see if I can find one real fast. Yeah, we got dark blue. Cool. You're different. You'll work. It's dark blue. Probably dead. No, it works. Cool. So dark blue is this point, right? The resistor KJ. Hey, I know someone named that. But KJ down here. We want to figure out the power of KJ. That's gonna be funny to me. It's equal to current. We know that. Times the voltage. We don't know that. Hey, we can figure out voltage. Same thing. V equals IR. V equals IR. We know that the current is 0.75. We know that the resistance is 6. So we get out our calculator because we're lazy, and 6 times 0.75 is 4.5. So the voltage is 4.5. Okay, that means we now can figure out the power of this 4.5 is the voltage times the current. So multiply that by 0.75. And we get 3.4 when I round watts. Now I know that a lot of you are going to be shocked by this, but that means this component also explodes. This has been a bloodbath so far. But that's why we normally use 220 ohms to like protect stuff, although this is a car battery voltage. But anyways, we normally use a larger resistor than 6 or 8 or 10, because these are really small values for resistance. They're not going to do much, which means you're going to draw a lot of watts. But next, we got these two. So, we need to figure out first off the current. Now, luckily we know the voltage between these 2 points has to be the same, right? Because they're parallel. So, can we figure out how much voltage is left? And your answer should be yes. We have a voltage here and a voltage here, right? This 12 volts lost 6 and then lost 4.5 more. This has to be the made up. This has to be what remains, right? Whatever voltage remains has to be going through these 2 resistors, because that's conservation of energy. So we get out to 12 minus 6 minus 4.5. We get 1.5 volts. Not much left, but there is some going through here still. So these 2 resistors both receive, I know this is becoming clustered, right? And I apologize, but that's why I use different colors, hopefully. Both these resistors receive a voltage of 1.5 volts. There's 1.5 volts being split between these 2 resistors, which means they both get 1.5 volts. Now, as long as we can figure out the current, we can figure out the power. So that's good. That's what we want. So current, how do we figure out the current for each of these? I know a lot of you are like, well, I mean, we've been using either Ohm's law or PIV. So if PIV gives us the watts, we're going to use Ohm's law. You're going to use Ohm's law. So we're going to use Ohm's law. So Ohm's law will be, let's see, this is the EF resistor. So VEF is equal to I called it 1. I'm going to stick with 1. R EF. So let's plug in numbers. So this resistance, this current will give us this voltage. Sorry, no. This voltage and this resistance will give us this current, right? Because the current splits. It's different. It's not this. So let's figure that out. So we know that 1.5 volts is equal to the current, which is what we want to solve for, times the resistance of 3. So we're going to get that the current is 3 times less than 1.5, so you can divide by 3. You get 0.5. This becomes 0.5 amperes. Cool. So that's the current of this first resistor. That did not answer our question though, so let's do that over here. So I'm running out of room. Yeah. So now we know that power of EF is equal to the current times the voltage. Well, the voltage is still 1.5. The current is what we just solved for at the 0.5. So 0.5 times 1.5 gives us 0.75. Now, I know a lot of us are going to be sad by this, but that means it almost lived, but it also totally exploded. Although there's tolerance ratings and probably would honestly live for a little bit and slowly burn out over time. So it wouldn't be as immediate as the rest of these. Last one we have right here is the second current. We're going to figure that out. We know it's voltage. We know it's resistance. So we're also going to use Ohm's law. So we're going to use Ohm's law. So I just rearrange it automatically. I of GH. That's going to be equal to voltage divided by resistance. We know the voltage and resistance in this case are 1.5 volts because it's shared between those two. Resistance is 5. This one might actually live. 1.5 divided by 5.3. So the current for these is 0.3 amperes. Next, we want power. Power, again, let's use the letters, GH. Power we know is PIV, which is current times voltage. Current, 0.3, voltage, 1.5 still. So 0.3 times 1.5. That gives us 0.45 watts. That is actually less than 1/2. I know a lot of you are excited for this part. I know a lot of you have been waiting on this, but this one lives. Yay! And this one dies, and this one also dies. It's a sad, tragic day in the world of these resistors. They all explode except for this one. Though in a real life situation, likely one of them would explode, and then for the others from exploding, it'd probably be the one that received the most watts to explode first, because it would be the one that'd be most overcharged. This one would probably be the one to explode first, and then protect the rest. Probably. Maybe. There's a lot of factors in there. A lot of factors. Cool, so we did that. That wasn't too bad. It's the hardest problem on the review for sure. It'd be one of the hardest problems on your test, but it's not too bad. It's not too bad at all. Next, we got everyone's favorite thing ever. Sketch a parallel circuit. And you love this because you're drawing a picture. Can't get much better than that. Now, when I say sketch a parallel circuit, technically, if you're going to be the one you're going to build, you're going to do a series resistor, and then the LEDs are going to be in parallel. But since this says sketch a parallel, all of these are going to be in parallel. That's because that's the wording of the problem for me. I would honestly take either on the test because in real life you would put the resistor in series. You just would. So I'm going to use green. So we got a battery, and it's in parallel with a resistor that is in parallel with an LED, that is in parallel with an LED, that is in parallel with an LED. I know a lot of you are shocked by this. And there we go. Now, if you use conventional current, or depending on what kind of current you use will affect which way the LED is facing. It's fine. Don't worry about that. We're just starting. So, label the components was said in this. So I'm going to label these components very creatively. Diode 1, diode 2, diode 3, resistor 1, and your battery, which I will call battery 1. Sure. I want to make this a little thicker, I guess. Yep, there's my sketch of the schematic. Hopefully that makes sense. This last one we need to build, and I need to get parts for this because I do not have them, so I shall be back. So now we're going to build a parallel circuit. Again, there are 3 different circuits you could have a choice of, but parallel is easiest, for sure. For sure. So some things you need is, of course, LEDs, wire. In this case, it's a little 9-volt battery clip. 9-volt battery. Don't need the screw that's somehow in my pocket, but let me find those wonderful, amazing resistors. Now, you could use a lot of different values of the resistor. The higher the value, the dimmer the LED. I recommend highly staying under 10K because that's getting a little too large. So I'm going to use 270s. 220 are nice. They work great. Don't go much lower than that because you have a tendency to overheat, murder your LEDs, and that's sad. So I'm going to build this parallel circuit 2 different ways. First way will be like this. We'll use one resistor, and we'll put it in series to the battery. Now when I say parallel LEDs, I mean the LEDs are parallel, but of course this resistor is actually in series to the battery. But maybe more details than most people care about. So we're going to go clippy clip, clippity clip, and we'll connect this to the battery, although we don't have to do it now. I'm going to do it now because it doesn't really matter for what we're doing. So it's connected. Next, you're going to grab a wire. Now, I have wires all around me. Hopefully, one is actually usable. Yep, this one will work. Stabby in and stabby in. So we got negative, and we got a negative. So now, by doing this in this situation, if I put these on the power rails, this positive makes this entire column positive. This negative makes this entire column negative. So when this green wire is hooked up to this negative, which you might have trouble seeing, this means that when I plug it in over here, this entire row is negative now. And with this resistor, since it's positive, it means this entire row right here is positive. So now when we grab some LEDs, I'm going to pick the yellow ones because that's I have a lot of them left. So yellow people apparently don't like. That's So don't forget, when you grab an LED, the long leg is positive, the short leg is negative. Also, the flat end is negative. So let's put the legs back together. So yeah, this long leg is positive, short leg is negative. So we're going to go ahead and put the long leg on this positive resistor, the short leg on the negative of the wire, which a little bit more. Yeah, okay. Someone put a dead LED back in the box. So let's redo that. That happens all the time when you have freshmen. But so this is the long leg, positive, short leg, negative. Put this down and stepify it into the board. Boom. You got one LED. Same thing, long leg, short leg. You got 2 LEDs, long leg, short leg. You got 3 LEDs. So, there's a parallel circuit, as in the LEDs themselves are parallel. They're all in this row. Now, if I pull one out, pull one more out, and leave this one on, you can tell the parallel because they stay lit even when the other ones are removed. They're series, it would turn off after you remove them. So this one, right? As long as it's in this 2 rows, where this is positive, where this resistor is, and this is negative, where this wire is, as long as it's in these 2 rows, wherever I plug it in, it should light up. Let me make sure I line that up when I do this. There we go. Wherever I plug this in, it should in fact light up, regardless of where it is between these 2 rows. These are negative and positive. So that is one way to build a parallel circuit. Again, resistors is technically in series, but parallel circuit for the LEDs. Another way, we yank that out, we yank you out. We're going to build this in what I call backwards. So we're going to move the power over here, so now it's going through the resistor. Because these are in a line. It's going through that resistor. This is going to go into negative. We'll put it down here maybe. So now, this is positive, but it goes through a resistor. This is negative. Make sure you have a resistor if you do this, otherwise all your LEDs will explode, and it'll be tragic. Anyway, so we're going to put these in now. Once you have it set up like this, you can just straight up put them into positive and negative, and they will light up. The reason why these don't explode from this is because, again, the positive of the battery is going through the resistor to reach these LEDs. If don't have that resistor. They will, and it's sad, tragic. So make sure that, like, prove that this actually works for 3 of them. We're going to use this 3rd one, and that's the review on video. I think this is backwards, actually. Let's find out. No, it's right. So there you go. So there is a parallel LED circuit. We did some math. Hopefully you're ready for your circuit test. That is next week. And you can build both a circuit. You can do some math. You can just solve some simple circuit problems. And of course, maybe not simple, but you know, there's way worse. Trust me, it only gets worse. But luckily, we're moving on to magnetism next week.